So your locus definition for your hyperbola is the set of all points so that the absolute value of the difference of your distances from your foci to a point on the curve is constant. And what I want to point out is this keyword right here, the difference. This definition is, this keyword is the difference between it and an ellipse. In an ellipse, it was the sum of the distances. This one, it's the difference. Okay, so we subtract them. So what that means, if you've got a focal point here and here, and notice that a hyperbola looks like reflected parabolas. They're two parabolic curves, but they like reflect each other. Your focal points, just like in the parabola, are inside the curve. Okay? So you've got two curves, you've got two foci, and the distance from one focus to a point on a curve minus the distance from the other focus to that same point, that's your constant. That's the constant that we're looking at. In an ellipse, it was the sum. In a hyperbola, it's the difference. So d sub 1 minus d sub 2 equals a constant. And we say the absolute value because it just depends upon which one, if you subtract this bigger one from the smaller one. That's what we're looking at. And that's what I was trying to depict here. However, I think it's a little bit difficult to really see. So instead of those, I'm putting big blue parentheses around it just to show that this is the distance from the first focus to a point. And I'm subtracting the distance from the second focus to a point. So this is like your d sub 1 minus d sub 2, I guess is how you can look at it, equals d, equals your constant. And it doesn't matter where the point is on the curve or which curve. It's going to be the same value no matter what. Okay, that's just your definition. Now, just like the ellipse, we have two forms. We have a horizontal and a vertical. Okay, notice the subtle difference between the hyperbola and the ellipse is you have subtraction here instead of addition. Thus, the definition, it's the difference between those focal point distances. That's where it's going to come into play in the formula. That's the only thing that looks different about the formulas. Okay? However, I want you to notice that A does not depict the biggest number. A is always going to be first. A is always first. A is going to be kind of what we consider like our major axis, where everything is located, but we don't call it a major axis because it doesn't have to be the bigger number. It's always the one under the first, whatever variable is represented first. If the x is represented first, it's going to be horizontal, meaning we're opening up horizontally. If y is first, it's going to be a vertical hyperbola, which means we're opening up vertically. So I want you to make a note that A is always first. May not be larger than B. So in an ellipse, A is always the largest, not in a hyperbola. Okay. So that's another subtle difference. You've got subtraction here, and A is always going to be located first. That's always going to depict the axis in which we're working on. Okay. But just like the others, 2A is going to be the distance between the vertices. Okay, so I'm going to underline that in green, and I'm going to go back up to this picture, and I want to show you that your A value is going to be the distance from the center to a vertex. That's A, and that's A. So that's where we get the 2A from, all the way across from one vertex to the other. But once you know where your center is, you get that from your equation, from your formula. The A value, you count both directions to get to each vertex. And then C is the distance from the center to each of your foci. Okay? And to find C, I want you to look at this formula. This is just subtly different from the ellipse. Do y'all remember what this was for the ellipse? It was subtraction for the ellipse, and it's addition for the hyperbola. So it's those little bitty details that will drive you nuts. That's what your formula chart is for. So that's what I would make sure that you note on your formula chart. So we are adding, so it looks like Pythagorean theorem. This is to find C, the distance from center to foci. To find C, the distance from the center to the foci. So if I go back up here and look at this picture, C is going to be from here to here. That is C. From the center to the foci on either side. All right. Now, hyperbolas also have eccentricity. Formula is the same as that of the ellipse, C divided by A. However, because we are adding A and B, your C value is going to be a little bit larger. Therefore, our ratio is always going to be greater than 1. Because remember, the ellipse is between 0 and 1, and for a hyperbola, it's going to be greater than 1. Okay, now, the last thing that you need to know about these hyperbolas is we have asymptotes. And these asymptotes are what create the boundaries for our hyperbolic curves. It's how we know how wide to make these curves right here. So I want you to make a note of that, is that the asymptotes create the boundaries for the hyperbolic curve. And the equation of the line, these asymptotes are just lines. And students, this formula that you're given right here is just point slope form. And what it is you are taking the center of your hyperbola that you get from your formula, and then you've got your slope is the ratio of B to A, or A to B. Now this is another subtle difference that I want to point out to you. I want you to highlight the slope ratios. And I'm going to go over those in a little bit more detail whenever we start graphing, because it's a little bit easier to explain. But I just need to point out that from the horizontal to the vertical asymptotes, these are the reciprocal of each other. They are the reciprocal of each other, okay? So point slope form using the center for your point. And your slope is the ratio of your A to B or B to A. So it's the ratio of your A and B values. Okay, just depends upon if it's horizontal or vertical. So now what we're going to do is we are going to take this equation right here, and we're going to get all the information out of it, and I'm going to show you how this graph was derived by the information in this equation. Okay, first things first. Looking at the equation, how do we know if it's vertical or horizontal? Not everybody at once. Which variable's first? The x. So therefore it's going to be horizontal opening up on the x-axis. It's going to open up on the x-axis. Okay, so this is your horizontal. How do I know that it's a hyperbola and not an ellipse? Subtraction. There you go. That right there. So I'm just trying to get y'all used to looking at this stuff, because because when you get on a test and it's all on there together, that's when it's like, oh my gosh, you just forget everything. It goes out the window. So I want to point these things out now so you can be practicing on what to look for. Okay, so this is horizontal. What is the value of A? 2. A is always going to be your first, and B is 5. Okay. Your center is, looking at your formula right here, where would your center be located? At 2, 0. There you go. Okay. Now, to find the value of C, what is your formula? C squared equals A squared plus B squared. So what is our A squared? 4. What is our B squared? Okay, so it's 4 plus 25. We take the square root. We're going to get a positive and negative square root of 29. Not a pretty number. It's okay. Approximately, what would be the square root of 29? Something bigger than 5, just barely bigger than 5, because 29 is between the perfect squares of 25 and 36. So that means its square root is between 5 and 6. All right, but right now that's all we need to worry about, is that right there. Now, let's go over here to our graph. We've got our center. Our center is right here at 2, 0. Okay. To get to our vertices, since this is a horizontal, our vertices are going to be on our horizontal axis right here. I'm going to move 2 from my center to get to my vertex. 1, 2 to the right, 1, 2 to the left. Vertex, vertex. Okay, so I can look at my graph and I can go ahead and acknowledge where my vertices are. To think about it with the formula, we're adding, subtracting 2 from our center. So if our center is at 2, 0, I'm going to add and subtract 2 from my x-coordinate, which would give me the ordered pairs 0, 0, and 4, 0. And that's exactly where my vertices are located here. To get to my foci, if my vertices, if I have to add and subtract to my x-coordinate, I have to do the same thing for my foci with my c value. So I'm going to add and subtract the square root of 29, God bless you, from my c value, or from my x value there. Now, let's come over here and let's just take a look. We know that's just a little bit more than 5. So if I count to the right, 1, 2, 3, 4, 5, and then just a little bit more, you'll see a point right there. That is your focal point. And do the same thing to the other side. 1, 2, 3, 4, 5, and just a little bit more. There's your other focal point. So I'm going to highlight those so that you can see where they are. And I am fine with you just leaving your answer for your ordered pair just like this. If you wanted to, you could go in and say, or my point is at a -3, I'm just making up 0.2, 0, and 7.20. I'm not sure exactly what it is, but it's just around there. Okay, your asymptotes. Now, the asymptotes follow the formula. If you've got the formula, which you will have it on your formula chart, you can write it down and just fill in the blanks. So since this is a horizontal, our formula is y minus k equals plus or minus b over a times x minus h. Here's how this b over a comes to be. All right. Do y'all see this dotted box in here? This is the easiest way to get your asymptotes to graph, because this box was created by what we call our conjugate and our transverse axis. They're not called major and minor because in this case, A is shorter than B, but that's our main axis. So it's called our transverse axis. And we got it when we counted right here, 2 and 2. That's our A value, A and A. But then our B value is going the other direction. It's going vertically. So if I count 5 up and 5 down, what I've done is I've created this little box. I can close that in. I go out as far as A. I go as high and as low as my value for B. And if you notice, your asymptotes run through each corner of that box and through the center. That is one of your asymptotes right there. And then it runs through the other corners through the center as well. Okay, so if you remember to find slope, to find the equation of a line, you need your slope and your y-intercept, right? Well, I can look at this and I can see that I cross my y-axis at -5. And I can also see that my rise over my run is up 5 over 2. Up 5 over 2. Well, that up 5 I get from my B value. My over 2 is what I get from my A value. So that's technically what it is. It's just those values together. Now, if I'm going to plug the number straight into the formula, my K value is 0, so it's just Y minus 0, which is Y. My plus or minus, my B value is 5, my A value is 2, parenthesis X minus 2 for H. And this is my equation for both lines. Because if I'm going to write the equation for the line and I use slope-intercept form, I have to do two separate equations, because this equation for this line has a y-intercept of positive 5 and it's got a negative slope. If you go ahead and use the formula to write this, it incorporates both of them in one to make it a little bit easier. So the formula for this, I think, will help you out if you have to answer the question, write the equation for the asymptotes. But I like to create this boxed in area so that I can physically see how my asymptotes are supposed to run. And then once I have that, I graph my curves by starting at my vertex, and I go out and I follow the asymptotes. When you got those asymptotes graphed, your curve just goes right along those asymptotes starting at your vertex. And then you've created your hyperbolic curve. Okay? A lot more tedious than the others. I want to practice this on example 2 on the next page. However, I forgot to fix something in here. I wanted this one to be vertical because I wanted to do an example of a horizontal and a vertical one. So in your on your example, can you change that X to a Y and your Y to an X? Because I want to make sure we do them two different ways. Yeah. Okay. Looking at this now, we've got the Y first. So since the Y is first, this is going to be a vertical hyperbola. So it's going to be opening up and down. Now, which one of these is A? The first one. The first one is always A in the hyperbola, and it happens to be the bigger one. So A is 4, and B is 3. All right. And where is my center located? 0, 0. Always make sure when you write your center, be very careful, because this one it's easy because they're both 0. But when Y is first, make sure that K value is the second one, okay? Because a lot of times students get their center flipped whenever Y is first. Okay, so that's a common mistake. So I'm going to plot my center at 0, 0, and I'm going to go ahead and use these values here to make my little boxed in area. A equals 4. That is my transverse axis, so I'm going to go up because it's vertical. 1, 2, 3, 4, plot a point, and then go down 1, 2, 3, 4, and plot a point. Those are my vertices. Okay? Now then, the 3, that's going to be horizontal. So I'm going to go, that's my conjugate axis, out 1, 2, 3, 1, 2, 3. And then I'm going to start at that negative 3, and I'm just going to count, think of your slope. I'm counting up and over to this point. I have to go through it and then back down through this point of my boxed in area, down and then back to the left and then back up. So those 4 points, those are kind of like the center of your boxed in area, okay? And your asymptotes are going to run through those. And you can go ahead and graph those in there if you want to get that done. And I know then that my my hyperbolic curves are going to run along those asymptotes. What you got to make sure of is when you're graphing this, that you graph within the right space, because sometimes people forget which direction it's going and graph it going the wrong direction. So there's a whole lot of graphing we've gotten done without having to do really any math yet, okay? The focal point, though, to get our focal point, we do have to find C. Okay, so to find C, that is A squared plus B squared, and then you have to take the square root of it. So our C value is actually going to be a positive and a negative 5. And we're moving from our center. 1, 2, 3, 4, 5. So here's my focal point here. And then I've got one the other direction. 1, 2, 3, 4, 5. Right here. And notice those focal points are inside your curves. The focal points are always going to be inside the curves. Now, as far as writing down the location of everything, our vertices, we know that we counted up and down from our center. And since we went up and down, we added and subtracted 4 from the y-coordinate. So our vertices are located at 0, 4 and 0, negative 4. Our foci are up and down as well. So since we added and subtracted from our y-coordinate, we're going to add and subtract from our y-coordinate for our foci. So it's plus or minus 5. Or we can say 0, 5, 0, negative 5. And if it helps, by this C value right here, I want you to write distance to foci. And if it also helps, for this one right here, put A equals distance to vertices. And then our asymptotes. These are vertical asymptotes. So y minus k equals plus or minus A over B, because it's always rise over run. And in this case, our rise is going to be 4 and our run is going to be 3. X minus h. So when you plug those values in for h and k, since they're both 0, we're going to end up with y equals plus or minus 4/3 x. And that is going to be your equation for your asymptotes. We don't have enough time to finish example 3, but I'm going to start you on it, okay? I'm going to start you on it. Example 3, this is in general form, and we have to put it in standard form. So I need to show you something. This is important. When you're putting this in standard form, just like the others, you have to group your x values together. Oops. I only have an x to the second, so I don't have to complete the square for it because there's no x to the first. But this is where you got to be careful. That minus 3y squared plus 30y, when I complete the square on that, we have to factor out this negative 3. I went ahead and added my constant to the other side. Now I'm going to complete the square. I factor out the 12 out of my x. Right here, I have to factor out a negative 3. And when I factor out a negative 3, what that leaves me with right here for this y value is a negative 10y. And then when I complete the square, what would my value for c be? 25. There you go. Equals 111. Okay, now, I did not complete the square for x, so there's nothing that I added an extra for it. But this is where you got to be careful. Remember how if you take out a coefficient, you have to multiply it times this term when we completed the square? I want you to acknowledge, though, that this isn't just 3. This is negative 3. So it's negative 3 times 25 is a negative 75. So on the left side, I've really added a negative 75. So that means I have to add a negative 75 to my other side. And this is what gets a lot of students right here, okay? It's just another little subtlety that can really mess things up. So now we've got 12x squared minus 3 parenthesis y minus 5 squared. I'm just writing it as the in its factored form. Equals, and 111 minus 75 is 36. Now, just like the ellipse, we have to set it equal to 1 for the hyperbola. So what do I do to get it set equal to 1? Yep, so I'm dividing both sides by 36. So on this side, 12 goes into 36 3 times, so that's x squared divided by 3 minus 3 goes into 36 12 times, so you have y minus 5 in parentheses squared over 12 equals 1. Okay. And then from this, you will get the information that we need. So, just looking at this, where is your center located? 0, 5. Okay. Can you find the value of C? What do you do to find C? A squared plus B squared. So A squared is 3, B squared is 2. So you've got plus or minus the square root of 15. So approximately, what is the square root of 15? 3 point something. 16 is 4. The square root of 16 is 4, so it's almost 4. So it could be like 3.8, 3.9. Okay? All right. to find your vertices, okay? To find our vertices, we have to take the square root of our A value. And the value of A is 3, so we have to move plus or minus the square root of 3. Now, is this going to affect the X or the Y coordinate of our center? How do we know? Because our X is first, right? It's going to affect our X. So we've got 0 plus or minus the square root of 3, comma 5 for our vertice. Okay? And then our foci. We're going to move a plus and minus square root of 15 from that same coordinate. So it would be 0 plus or minus the square root of 15, comma 5. And then our asymptotes. Our asymptote. Y minus K. What is K? 5. There we go. Equals plus or minus. Now, is this going to be A over B or B over A? B over A. And our B value is the square root of 12. And it's over the square root of 3. X minus 0. Now, this is not good. I don't like this right here. We should clean that up. Since these are both under a radical, what's 12 divided by 3? 4. What's the square root of 4? 2. So this is actually y minus 5 equals plus or minus 2 x. And that would be the cleaned up version. Okay? All right. And I'm going to stop there. So now, I did not talk any more about the